Good morning. Let's begin lecture 25. Today is the day we focus on all pass lattice with the hope of addressing the issue for the two channel maximally decimated filter bank. How do we eliminate amplitude distortion? Again, as I mentioned, this is not the end of the, or this is not the end goal. The end goal is something beyond. We are basically building up a set of tools that will help us go beyond the magnitude distortion itself. But for now, the focus is on the magnitude distortion. So, quick run through of the key results. We are talking about the two channel filter bank, aliasing eliminated through the choice of the filters. What we are left with is if you do the polyphase decomposition, the transfer function is 2 times Z inverse E naught of Z squared E1 of Z squared. We are not going through the traditional approach. We are going to look at the possibility of representing the filters in terms of a sum and difference of all pass functions A naught and A1. In that case, the transfer function will eliminate aliasing. Now, we are working backwards. If we have all pass filters, how do we get to the good low pass filter? So, I think kind of meeting it from both sides. So, this is what we know already. So, what we are developing now is the theory of all pass functions, which then says how do I construct good low pass and filters for the filter bank. So, the study of all pass filters, all pass functions introduces a few notation which is very helpful for us. The first one is paraconjugation, and paraconjugation represents conjugation of the coefficients and Z replaced with Z inverse, and we said that this basically gives us two alternate definitions of paraconjugation, where you do conjugation of the coefficients and Z replace Z with Z inverse. That is a direct representation. The other one is you conjugate the entire function, which means that Z being complex will also get conjugated, and then you would have to replace Z with 1 over Z conjugate. So, that is the other representation that we have represent. So, hopefully conjugation or the paraconjugation is something that is you are comfortable with, and we will use this in the development of the theory going forward. An important result is that the paraconjugation is the analytic extension of conjugation on the unit circle, which basically says that if I have h e of j omega magnitude squared, then this can actually be written as h of z h tilde of z, z equal to e of j omega. That is on the unit circle, because that represents conjugation. But once you go outside of the unit circle, then it still has the same flavor of taking the magnitude squared, but it is now h of z h tilde of z, where h tilde represents the paraconjugation. There were 3 properties of all pass functions which we were trying to prove. The first one is the fact that, let me just jump ahead, that all pass functions are lossless in terms of the energy of the input signal being preserved at the output. Second one is the maximum modulus property, where h e of j omega magnitude is equal to 1 on the unit circle, it is less than 1 inside outside the unit circle, and greater than 1 inside the unit circle. Again, this is the property of analytic functions and the analytic extensions that we have done, but please take this as a result in case you have not studied the maximum modulus property in the study of complex variables. The third property, of course, is h e of j omega. If you look at the phase of that transfer function, then we said that the derivative with respect to omega is less than 0. That means it is monotone decreasing function, and this is something that is a property of causal stable all pass functions. Okay, so this is true for causal stable all pass functions. Okay, so I am assuming that these are properties that you can verify if needed and be able to use it, causal stable all pass. So, this more or less gives us a good framework for the all pass functions. Let us now dive into what is it that we are going to need going forward from here. So, we said that magnitude h e of j omega magnitude squared can be written or represented as h of z h tilde of z on the unit circle. So, paraconjugation on the unit circle. Now, this also tells us that whenever I take some function of the form b of z divided by z power minus n b tilde of z, this is going to be all pass, because on the unit circle they are conjugates of each other, and therefore, the magnitude will be equal to 1. Therefore, this is the form of the transfer functions that we are interested in. The other element which is also sort of emerges from here, that if you have all pass functions and they have the structure shown above, this also means that if I have a pole at z0, pole at z0, then this necessarily requires, because of the structure, there will be a 0 corresponding to, because they are both of the same polynomial. So, there has to be a 0 at 1 over z0 conjugate. So, there is a reciprocal conjugate relationship between the poles and 0. So, there is, so please make a note of that, reciprocal conjugate locations. And this is universally true, whether it is a stable all pass or not, you must have this property in order for it to satisfy. And then we also justified that how this pole and 0 are on the same radial axis, and therefore on the same radial line, and therefore enables us to work with this. And of course, we have the 3 properties. Okay, now we would like you to study the following structure, because it is going to take us into the domain of all pass structures, and the it is very insightful. It is a simple exercise, but also a very useful exercise. So, if I have a structure which is of this form, let me represent this transfer function as g subscript n minus 1 of z. Again, the subscripts will become clearer once we have gone through. There is a delay element z inverse, and then there is going to be a crisscross, which is a slightly different crisscross from the FFT butterfly that you are familiar with. So, please draw the arrows in the right direction. So, this one is a path going from the input to the output, and this one is a path going from the output to the input. Okay. So, I need a minute to get my lines straight. Okay. So, 2 multipliers. So, notice that this is a feedback type of structure. Let me draw the input line, let me call that as u of n, the output line y of n. Make sure all the branches are labeled with arrows so that we have no confusion. This is minus k subscript n, and this is k subscript n conjugate. Okay. So, basically my input is u of n, output is y of n. I would be interested in computing the transfer function y of z divided by u of z. That is my ultimate goal. So, let us work towards that, and it is helpful for us to define an intermediate signal v of n, because that helps us get the transfer functions. So, let me just write down the steps. I am sure analyzing a lattice structure is something that you are familiar with, but just as practice, let us do that together. Please help me write the equation for v of z. So, basically v of n, okay. V of n is u of n plus v of n passing through gn minus 1 of z, z inverse, and minus kn. Both of those get added together. Basically, these solid dots means that they are either signals are adding, or if it is a branch from which they are branching out, the same signal is going on both those branches. So, v of z is equal to u of z plus v of z itself passing through gn minus 1 of z then Z inverse, and then minus k subscript n. Okay, so if you were to group the terms, this would be V of Z into 1 plus k n Z inverse g n minus 1 of Z is equal to U of Z. Okay, that is equation 1. Okay, so please do the same similar exercise and verify equation 2, which says y of Z can also be written in terms of V of Z, can be written as V of Z into k n star plus Z inverse g n minus 1 of Z. Okay, so that is equation 2. So between equation 1 and 2 we have the essentially the representation that we are looking for. So y of Z by U of Z can be written as k n star plus Z inverse g n minus 1 of Z divided by 1 plus k n Z inverse g n minus 1 of Z. Okay. So, again basically it is just analysis of a lattice that has got some feedback paths. So, therefore, the transfer function will be an IIR transfer function, basically we will have numerator and denominator, and this is what we have obtained. Okay, this is let us call this as equation 3. Now, from equation 3 it is just a simple rewriting of the equations to verify that Z inverse g n minus 1 of Z can be written as g n of Z minus k n star divided by 1 minus k n g n of Z. Okay, just basically rewriting the equation. So, maybe we call this as equation 4. So, 1, 2, 3, 4 from the lattice structure that has been given to us. Okay, now here comes the interesting part. Now, supposing g n of Z is a causal stable all pass function of order n, g n of Z, if g n of Z is a causal stable all pass, okay, causal stable all pass of order n, okay. So, here is the key result. Then there exists a coefficient, there exists k subscript n, a coefficient such that with mod k n less than 1, strictly less than 1, and so basically there exists a k n such that mod k n will be less than 1 and g n minus 1 of Z is also a causal stable all pass of order n minus 1, all pass of unit magnitude, that means there is no gain, okay, that maybe is not as important, but more important it has got one order 1 less, order n minus 1. Now, we need to verify this. Okay, is the statement clear? Lattice structure obtained the g n of Z in terms of g n minus 1 of Z. Now, what is g n of Z in the previous graph? Let us just go back and label this. So, this is what we are labeling or we are calling as g n of Z. So, basically the transfer function in this input output relationship, or if you are used to viewing it as this is the transfer function looking in. Okay, input signal going in, output signal coming out, and again in the 2 port networks you would have studied transfer functions of this type. This is the representation. Okay, so our task now is to quickly verify this. Of course, if you have worked with lattices, this would be quite an easy task, but even if you have not worked with it, it is a very interesting exercise. So, let us look through that. Okay. So, Gn of z is a causal stable all pass function. So, we would like to write down Gn of z. The form of Gn of z is of the form b subscript n of z, just to indicate the order of the polynomial. The numerator would be z power minus n b n tilde of z. That would be the, and if you wanted to write down the polynomial b n of z, we would write it in the following manner: b n comma 0, that means it is a 0th coefficient of the polynomial, plus b n comma 1 z inverse plus b n comma 2 z minus 2 dot 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 plus b n comma n, the nth coefficient of the polynomial, z power minus n. Okay. Now, if I substitute this form in the expression that is given to us in 4, substituting 5 in 4, what we get is z inverse g n minus 1 of z is of the form, the denominator is b n of z, did I get that correctly? 1 minus k n, yes, correct. So, b n of z minus k n b n tilde of z, that will be the denominator. Numerator will be z power minus n b n tilde of z minus k n star times b n of z. Basically, I have just substituted the expression for g n of z and just rewrote the equations. I am sorry? Oh, absolutely. Thank you. Yes. Okay. So, what I would like to do is focus in on this portion of the expression. Okay. So, I am going to write the polynomial, I am going to write it in the following way. I am going to write the coefficients as a vector. Again, you will see in a minute why that is helpful for us. So, the coefficients are b n comma 0, b n comma 1 all the way to b n comma n. Okay. So, in terms of the coefficients, this is the coefficient of z power 0, this is the coefficient of z minus 1, this is the coefficient of z minus n. Okay. That is basically that is b n of z. So, this is a representation of b n of z. Let me use a different color. This is a representation of b n of z. Okay. Now, the second term is b n tilde. So, I will do a minus k n and I now have to represent b n tilde and z power minus n. So, basically the coefficients will go in reverse order and they will get conjugated. So, the topmost coefficient, the coefficient of z power minus n now will be b n comma 0 conjugate, then all the way down, and the last coefficient will be b n comma n conjugate. Okay. That is a representation of z power minus n times b n tilde. This is the representation of z power, I am using a color that is already there, let me use blue. So, this represents z power minus n b n tilde. Okay. So, put them both side by side, it is very easy to sort of see what the coefficients come out to be, and you can do something similar for the numerator also. But the important thing is the following. What did the statement say? That there exists a k of n with mod k n less than 1 such that the newer the Gn minus 1 has got a is first of all lower order, and so here is the possible choice. So, possible choice, that means you have to just show the existence possible choice for Kn. So, if I choose Kn to be equal to Bnn divided by Bn comma 0 conjugate, okay, Kn to be Bnn minus. So, notice that that means the first term, the topmost z power minus n power will get knocked off. So, this more or less guarantees that the denominator polynomial in 4, or in, you can also label this as 6, denominator polynomial in 6 has order n minus 1. Okay, this choice will ensure that the order of the polynomial gets decreased. Okay. Now, spend a minute to tell me what the coefficient on the numerator will be, So, basically it will be z power minus n Bn of z, that is sitting there, minus Kn conjugate times the coefficients of Bn of z. Okay. If you write that down and substitute what you have here, you can verify that in the numerator term, yes, the constant term gets knocked off. In the numerator, what you will get is Bn n comma n's Bn comma n conjugate minus Bn comma n conjugate. This is the coefficient of z power 0. This is the coefficient of z power 0 or the constant term, and this is equal to 0. Okay. So, the choice that we have made, choice of Kn equal to minus equal to Bn comma n divided by Bn comma 0 conjugate, Bn comma 0 conjugate within the structure and the framework that we have been working with. This guarantees the following: the numerator has got the constant term equal to 0, numerator polynomial has constant term equal to 0, constant term equal to 0, denominator polynomial has got order n minus 1, has order n minus 1. So, therefore, we can write the transfer function z inverse g m minus 1 of z, that is the transfer function that was there, and the numerator has got order 1 less. So, therefore, I can write this as some z inverse divided by, it is not m, it is n. Okay, some denominator polynomial which is Bn minus 1, because it is a lower order polynomial, and the numerator is some polynomial of order n minus 1 also, because you have factored out z inverse, right, because it will have starting from z minus 1 all the way to z power minus n. If you factor out z inverse, that will also become a polynomial of order n minus 1. Okay. So, now please go back and verify that z inverse a n minus 1 of z from the expression is actually equal to z power minus n b n tilde of z minus k n star b n of z. This is the expression for the numerator of the, and you can verify, again it is absolutely straightforward, but very, very important that you verify that this gives you the following result, that a n minus 1 of z is actually equal to z power minus n minus 1 Bn minus 1 of Z tilde. Okay. Very important that you are able to verify. It's straightforward, but please do verify that this is the case. If this is the case, then we have the following result. This basically means that Gn minus 1 of Z is of the form Bn minus 1 of Z power minus n minus 1 Bn minus 1 of Z tilde. Okay. Let me give you a minute to sort of assimilate that if you want to make any additional notes. So, let me go back to the previous structure. The structure is defined as follows. We have assumed that Gn of Z is a causal stable all pass function. So, which means you can write it in the using the paraconjugation form. If you do that and choose your Kn appropriately, okay. So, we have not yet shown that mod Kn is less than 1. We have not yet shown that Gn minus 1 is stable. So, those are yet to be shown, but at least we have come to the part of saying that, okay. So, now at least we have shown that Gn minus 1 is also all pass. Gn all pass, causal stable all pass, we have been able to show that Gn minus 1 with the appropriate choice of Kn will come out to be an all pass function.
Sir?
Yeah.
The second last equation.
Yes.
Is that how you are defining it, or
which one?
An minus 1 of Z
yes.
equals Z?
No, you actually have to verify. So, basically we have shown what Bn minus 1 of Z is, right. We have shown what the expression for Bn minus 1 of Z is. Using that substitution for that value, similarly you can get an expression for the numerator, and you can show that the numerator. So, yeah, this is not an assumption, this is to be shown. This is to be verified. You have to verify that this is true. Yeah, if you assume that, then of course it will become all pass. So, but it's actually something that it's not difficult to verify. Okay. Now, a very important observation that comes now. Again, this is where the beauty of the lattice structures lie, and all of the theory that you have studied in signal processing and networks and systems, all of it come together. Let's take a closer look at the polynomial Bn of Z. Bn of Z is the denominator of a causal stable all pass function. So, it has to have all poles strictly inside the unit circle. So, all poles strictly inside unit circle, inside mod Z equal to 1. Okay. So, now Bn of Z, we have written it down as Bn comma 0 plus Bn comma 1 times Z inverse dot 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 plus Bn comma n Z power minus n. If I factor out Bn comma 0, again may seem like a trivial step, but it is very important in the overall. This becomes Bn comma 1 divided by Bn comma 0 Z inverse all the way up to the last term is Bn comma n divided by Bn comma 0 times Z power minus n. Okay, you may wonder, just factoring one element out does not make any difference at all. But if you were to factorize the polynomial in terms of its poles or in terms of its zeros, B of Z has its zeros, then if you were to write it down in the following way, product, there are n, it is an nth order polynomial, so there are n zeros, I equal to 1 through n, 1 minus Zi Z inverse. Basically, I am writing it in an alternate form, and now compare it to this expression. Okay. You can verify that modulus of Bn comma n comma Bn divided by Bn comma 0 is actually equal to the product of the poles, the radius of the poles. Okay. So, this is equal to the product of I equal to 1 through n mod Zi. Okay. Now, we are told that the all pass is causal stable. So, all mod Zi less than 1 for all values of I equal to 1 through n, and this, if you remember, is also the definition of Kn. So, this is equal to mod Kn. So, the second assumption we have also validated. First assumption was that the lower order all pass was obtained. So, mod Kn less than 1 is also satisfied because Gn minus 1 is a causal stable all pass function. Okay. Now, just hold on for the next step, because this is also very, very important. Now, the expression for Gm minus 1. So, basically if you go back and look at, I do not remember the equation number, but I will just request you to look at it up. Z inverse Gn minus 1 of Z we wrote down as Gn of Z minus Kn star divided by 1 minus Kn Gn of Z. Okay, we wrote this down. So, I want to now look at the poles of Gn minus 1 of Z. Poles of Gn minus 1. I am hoping to see if I can show that the poles of Gn minus 1 are inside the unit circle. That means stable gave me stable of order less than 1 in the lattice structure. So, Gn minus 1 poles of 0, supposing is a pole at Z naught, then supposing consider a pole at Z naught, consider a pole of Gn minus 1 at Z equal to Z naught. This would imply 1 minus Gn k 1 minus Kn Gn of Z naught is equal to 0, that would have to be 0. From this we can also verify that mod Gn of Z naught is equal to 1 over mod 1 over Kn, correct. I have just rewritten that equation. Mod Kn is less than 1. So, 1 over mod Kn will be greater than 1. So, this will be greater than 1. Now, what can you tell me from maximum modulus theorem? It has to be inside the unit circle. Z naught has to be inside the unit circle. Okay. So, this implies Z naught lies inside unit circle. Okay. So, Gn minus 1 is stable. Okay. So, this is a very useful structure. So, what it says is, if I have Gn as a causal stable all pass, I can find a Kn such that Gn minus 1 will be one lower order, it will also be causal stable all pass. Okay. Now, you tell me by induction what can you take it to the next level. Gn minus 1 stable, I can find Kn minus 1 such that it becomes Kn minus 2, and of course, you can go all the way down, and the last term will be the most trivial all pass function will be a constant. So, if I were to generalize this structure, I get the following. Yes.
Why can't we say the Gn is rational, right?
Yes.
The numerator also can go to infinity inside, right? Gn of Z minus Kn conjugate.
So, okay. Let me just be sure. Okay, this expression Gn minus 1. I am sorry.
In that we are only saying the denominator going to 0 as a pole.
Right. When you have a rational transfer function. No. The numerator is a polynomial, denominator is a polynomial. No. When you rewrite it, you can rewrite it as polynomials. Basically, it's a polynomial on the numerator.
Gn of Z minus Kn star is rational.
Yeah, but you can you can rewrite it as a polynomial. Right. Look at it, because there is a relationship between the two. Okay, so here is the way we would look at it. I will have a input, there is a that crisscross form, I am just going to label this as k subscript n, and the delay is outside. Okay, so what is inside is only the crisscross portion. The transfer function of this would be gn minus 1, but now I am going to replace it with another lattice structure or crisscross, which is kn minus 1. This would be z inverse, this would lead to kn minus 2, kn minus 2 and dot dot dot. Dot 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 on the numerator and on the denominator side, and the last stage I will call this as k1. This is also a crisscross, and this goes to a transfer function which will be g naught. G naught, let us take it to be equal to 1. That is a trivial all pass function, just a constant, and what we have here is z inverse. Okay. So, what it says is that if I have a causal stable all pass function g n of z, causal stable all pass function g n of z, then actually we can obtain a lattice structure where we can show that all the kn's are modulus less than 1, modulus k lower case, or let me call it as k subscript I less than 1 for all values of I. Okay. We can also show the following, again it is a trivial extension of it, I am sure you can do that. If g n of z has real coefficients, real valued coefficients, then kn, which is a ratio of two of the coefficients of the polynomial, kn's will also become real. Then ki's are real, and the lower order polynomials gi of z I equal to 1 through n minus 1 are also have real coefficients also, have real coefficients. So, actually you can come up with a lattice that has got basically real coefficients everywhere. Okay. Now, here comes a very, very important observation. This also says that if you take this structure and ensure that mod k's are less than 1, then you are guaranteed that your transfer function will be all pass and it will be stable. Okay. Now, if you do anything with adaptive filters where all pass functions are involved, this is the structure you should be using, because all you have to keep in mind is that the kn's do not have magnitude greater than 1, and of course you can use. So, it is a very, very useful structure. Now, have you seen this structure anywhere other than signal processing? You have. You have seen it somewhere. There is something called Routh-Hurwitz criterion for stability of a transfer function. What do? You construct a numerator you take a polynomial, construct a numerator polynomial which is time reversed, and then you compute the k coefficients. What are those are just the reflection coefficients. That is actually what you do for the all pass structure. It is actually the test for stability of a polynomial. How do you test for stability of a polynomial? If you take any polynomial and just basically construct an all pass, take your polynomial to be b of z and then compute all the k coefficients, all of them come out to be less than 1, you are guaranteed that it is a stable transfer function, stable, all the zeros are inside the unit circle, right. And this is actually this is the basis for that test to actually basically there's a lot of theory that goes behind how do you prove the necessary and sufficient conditions and all that. We have kind of skipped that, but again to show you that this is a very useful structure that we have obtained. Okay, so all pass functions, structurally all pass functions, and what we can do with them are shown in this particular section. Okay, now very quickly I would like to introduce some additional terminology which is also important for us. I am going to talk about bounded transfer functions. Okay, again these are important for us in the study of filter banks, so that is why we are introducing them. So a function is said to be bounded if h of z is a stable transfer function, is stable, and it satisfies mod h e of j omega less than or equal to 1 or some constant, again for us 1 is as good, then we say that h of z is bounded. It is bounded in terms of the magnitude response viewed on the unit circle. H of z is a bounded transfer function because you are always looking at it in terms of its behavior on the unit circle. Now this clearly tells us that this is a well defined transfer function on the unit circle. It does not take very large values, it is a well behaved function, and then by analytic continuation you can get all kinds of extensions of h of z, but I will leave that to you. There is another subset of this which is called bounded real. Okay, bounded real transfer function, that is the class of functions where the coefficients of h of z are real. Okay, so again nothing very different. Bounded real transfer function implies a bounded transfer function with real coefficients. Okay, so bounded actually has got a very strict definition in the context of the signal processing framework that we are dealing with. Bounded transfer function with real coefficients. Okay, so we will be focusing on the class of bounded real transfer functions, very useful for us. Of course, the next one that I am going to write down is already known to you. What is a lossless transfer function? A lossless transfer function basically preserves energy. So basically it means that it is a stable transfer function and is all pass. Okay, energy is preserved. Energy is preserved. Okay, now I want to ask you to think about the following. Does this statement make sense? A class of functions that are lossless bounded real transfer functions, LBR. Does that make sense? It is a transfer function that preserves energy and is well behaved on the unit circle. Okay. So well, if it is a lossless and all pass, it has to be less than, or it has to be equal to 1 on the unit circle, but it has got real coefficients as well. Okay, so basically this would point to a causal stable all pass, with real coefficients, all pass with real coefficients. Okay. So just lossless could mean a all pass function with complex coefficients, and another reinforcement of the property is that we also want things that are bounded. Okay. Now here comes a very interesting extension of what we have been studying so far. We call a set of transfer functions as power complementary. Power complementary transfer functions, if they satisfy the following: h naught of z and h1 of z are two transfer functions. They are power complementary PC if they satisfy the following property: magnitude h naught E of j omega magnitude squared plus h1 E of j omega magnitude squared is equal to a constant. I would like to take it to be equal to 1 for all values of omega. We would like this property to be satisfied. And now we have seen this condition in the two channel case when I had linear phase. If I had could construct those pair of polynomials to be power complementary, then I would not have to be doing this magnitude constraint. It would come out to be in fact I would get perfect reconstruction, because I have already eliminated aliasing, eliminated phase, and now with if they had been power complementary. But you kind of see where we are heading. Now by analytic continuation, this basically means h naught tilde of z, h naught of z plus h1 tilde of z, h1 of z is equal to 1. Okay, that is the power complementary condition. Okay. Now, of course, if you can generalize the power complementary to more than two transfer functions. In the general case of power complementary transfer functions, we get the following: summation k equal to 0 to m minus 1 magnitude h k E of j omega magnitude squared equal to 1. So basically there can be m transfer functions which are power complementary. You just have to make sure that their magnitude squares when added up over all the functions is a constant that is that we have. Okay. Now very quickly we need to put several pieces that we have already studied together. Okay. Here is a result I just want you to quickly think about. We will put the pieces together in tomorrow's class. What is the ideal interpolation filter? Ideal interpolation filter, Nyquist filter. Okay, we said that this will be, if I want to interpolate by a factor of m, this will have a height of m, this is a frequency response, magnitude h E of j omega, it will go from minus pi over m to pi over m. If I take it to be a zero phase filter, then I get a infinitely long sinc function sin pi n over m divided by pi n over m, basically that is the sinc function form. Now, did we say something about the polyphase components of these ideal filters? Any observations that we had made? I believe we had made an observation about the polyphase components. Polyphase components. If you look at this structure, what you will find is that there is a polyphase component E naught of z such that E naught of n, the corresponding, is equal to 1 for n equal to 0 otherwise. Okay, that is the central point of the impulse response. That is the only one that is got. And remember, there will be 0 crossings at regular intervals. So all other coefficients will be 0. So this particular polyphase component is has got only constant coefficient. Okay. Now this has got a very significant importance in our study, and basically maybe that will come in the next lecture. The second element that we would want to build upon is the underlying interest that we have in the following. Our goal is to come up with a set of transfer functions h naught of z to be equal to sum of two all pass functions, a naught of z plus a1 of z divided by 2 h1 of z. Again, this is why we even studied about the all pass functions. h1 of z to be equal to a naught of z minus A1 of z divided by 2. Again, this is because of the relationships that exist between them, H0 and H1. So, basically if we can write it in this form, then we are able to get a lot of the results that come from there. So, what we will refer to as the all pass decomposition theorem. When can we achieve these conditions? All pass decomposition theorem. When can we write two transfer functions that are power complementary and will satisfy this all pass decomposition theorem? Again, this is a result that has been derived in the book by P.P. Vaidyanathan, chapter 5. I will use the result without proof, but again there is enough of the justifications for what we are going to be actually implementing. And so, what are we going to do now? We have studied all pass functions. We will now look at the solution that gives us a good set of filters which are H0 and H1, which can be used in an IIR 2-channel filter bank, and hopefully this maybe gives us some clues to go beyond, because this one will not eliminate phase distortion, this will have phase distortion. Now, we will sort of try to see whether we can look at the linear phase part and then the all pass part, and then say, okay, can I combine these two in some ways and get a perfect reconstruction filter bank, because I want to eliminate phase distortion and magnitude distortion in the solution that we are trying to work with. So, one more step and we will get a work towards the perfect reconstruction. Okay. After we do 2-channel perfect reconstruction, we will only briefly mention what it takes to do arbitrary channel perfect reconstruction. Basically, we will say how difficult a problem it is, and then once we finish that, then the last 2 chapters of the course, one will be on wavelets, the other one will be on OFDM. Okay, so, those are the 2 chapters remaining, and again what I would like to request is your cooperation to schedule the makeup classes. It has been very difficult for the TAs and me, because the studio is not available, or some student has got something or the other. So, the only options that seem at this point are October 28th is a Saturday and October 31st is a Tuesday. So, between those two we would have to make sure we make up 2 or 3 hours of missed classes, because only then we can finish whatever we have planned as part of the course, otherwise we will be left unable to finish what we would like to do. So, again we pick it up from here in tomorrow's class. Hopefully we will reach perfect reconstruction tomorrow. Thank you.